All right, so welcome to Module 3 of Software Engineering. We're going to dive right into it. So you can see the pre-class warm-up, which I like to start off with. And today I want to ask folks, what do they think of when someone asks you what it takes to be a great engineer? Or, what do you think of great software engineers? What in general comes to mind? And this could be somebody that you've worked with professionally, maybe someone you've had a class with, maybe someone you've seen a YouTube tutorial about or read a book. What are the things that make them so great? So I went ahead and thought about this exercise a little bit, and here's the thoughts that I came up with. Usually someone who's a great software engineer has experience, they have practice, knowing their foundations, studying, trying things and trying to break them, and really just understanding that in software, pretty much everything has a trade-off. So, folks who can sort of list the pros and cons of different approaches and understand there's no definitive answer, usually have a good sense of the problem that they're trying to solve. So these are just some of my thoughts and some things we'll want to think about in this course. Okay, so we are recording. Last class, just to review what we worked on, is that C++ is a multi-paradigm language. So we talked about one of those paradigms, which is object-oriented programming, using things like classes to structure our programs into different sort of user-defined types that have behaviors and data tied together. Okay, so we looked at some examples here with the window. We talked a little bit about how to structure and organize our programs, both in the sense of making things into classes, moving things into namespaces so they're sort of organized or logically grouped, and then even things about how to organize our file directory structure and use tools like make and CMake to build our projects to help us iterate on them. And finally, we explored linkers and third-party libraries. So we started thinking a little bit about code that other people develop that we might want to bring into our projects, and how exactly that happens with a tool called a linker, which glues everything together. Okay, and then finally, again, on the APIs, we looked at some examples with the Simple Fast Media Library. Okay, so some course logistics, things going on. Lab 2 is due, so make sure you have that. We're still working individually here. We're going to learn some design patterns today and a little bit more about object-oriented programming. That's going to be our task for today with a little walkthrough example. And just a note, last class during one of the live sessions, we talked about how to utilize Monday to Wednesdays. I wanted to throw out an idea and poll students. So our Monday, Wednesday sessions when we're meeting synchronously, the first 45 minutes is going to be, or 45 minutes an hour is going to be meeting as a group. And having this sort of large-scale discussion as we've been doing with the review of lecture on Monday, review of lab on Wednesday. And then the last 45 minutes I've allocated to signups for more office hours, just to get more coverage, make sure I have some specific times for my software engineering students, or you guys. And then in lab, we're going to work on implementing a design pattern and maybe a little bit more Git, but at least another design pattern here. Okay, so let's dive into lecture 3 on design patterns. So again, we started today thinking about what makes a great software engineer. And in general, as I mentioned, this comes from folks who've had experience or practice, or just a handle on the problem, okay? So, there are really a few key challenging problems in software engineering, and that software is always changing. So it's a sort of moving target, and many people work on the same software. So that can also make things challenging because you have to figure out how folks can collaborate. Now C++ languages similar to C++ have developed and evolved to help challenge some of these, or to help tackle some of these challenges, some of them which are human problems, like how many people work on the software, by giving us better abstractions for both writing software and how we reason about software. So again, I'm thinking about object-oriented programming today. So a little bit on object-oriented programming, again in C++, just to really get these ideas into us that, there's really two essential object-oriented programming concepts. There's many things that are considered object-oriented, but the real two ones, the big ones, are classes and inheritance. Okay, And both of them help us scale and build large pieces of software, which we can also collaboratively build with other folks on our team. So let's just start again with classes. I know we've looked at them a few times, but it's important to just really get this in our heads and understand the terminology. Classes in C++ are just a way that allows us to create a custom data type. And C++ structs are almost exactly the same, except that their privacy level is public. Okay, so when you create a class, everything by default is private, so that's a little bit more conservative. This is important when we talk about inheritance, which we'll get to. But again, the key idea with a class is it's a user-defined type, and we can have behaviors and attributes all together. Okay, so the member functions are all together, and then the member variables, the actual data within an instance of that class is there. Okay, so these custom data types that we're creating hide the implementations behaviors from a client using the class. So again, this just allows a client to worry about what member functions are available. They don't necessarily have to worry as much about the implementation for that class, so long as it achieves their job. Okay, so the picture on the right here shows one visualization of a class. So here would be an example of a student class, and no implementation code is shown, but this is one way, again, when we're designing APIs, thinking about how to make classes and what functionality they should have, we can summarize this in a visual manner. So here's a student class. It has data members and then various member functions associated with the student. Okay, so there's no implementation code here. Again, it's just a nice visualization here. So what this visualization is something called UML, the Unified Modeling Language. It's just a compact way to represent software systems. Because remember, I mentioned that building big software that we have to maintain is one of the challenges that we have to deal with. So UML can be one of our tools for helping us with that. It's not an end-all be-all tool, but it is a useful tool. I at least want you to understand, if not for reading other texts and papers to understand it's a UML diagram and what the different symbols mean. So again, it's just a modeling language, but really a visualization of our software. So on the right here is the class diagram, which we looked at here. These are just class diagrams. And then on the left side is the component diagram, which shows how perhaps different classes interact with each other. Okay, so we'll use classes in this course to represent class diagrams. Some of them will automatically generate, and you'll find that they're helpful when working with large teams. Okay, so here's just a quick sample of a UML for our class diagram. We'll look at these a little bit more in depth as we go, but the class name is usually listed at the top, usually followed by member variables. That's the data where you can store stuff. And then any member functions, your behaviors that can be done are then listed next in this UML box here. Okay, so that's what I want to talk about for classes. Again, just kind of solidifying this topic here. And then I want to move us on to inheritance, the second really big idea in object-oriented programming. Okay, so what is inheritance? It's the idea in object-oriented programs that we have one class here, a base class, and we can create a new class that's derived from a base class. Okay, so inheritance is very useful then for building more complex data structures. One, without us having to repeat code, but also for us to have this derived class also be a type of whatever this base class is that it is derived from. Okay, so I'll just make that very explicit with this note here, that's what's the importance here, that B is of a type A here because it inherits from it. Just like you are, a son or daughter, or, whatever of, someone, one of your elders, okay? So you can almost think of this in a family tree in sort of a biological way, a sort of type of, if you will. Okay, so we can also have different strengths or amount of power with multiple inheritance in object-oriented programming. So a derived class, so this derived class A can have multiple base classes, just like you can have multiple parents here. If you want to think about this again as a family tree. And we briefly talked about this, I believe, in one of the early lectures, that this is generally confusing because if class B and class C have a member function that's named the same, the one that class A gets is undefined. It'll either get B or C. It's whatever the compiler chooses. But it's also confusing, again, when we think about inheritance, of trying to think of class A as a derived class of B and C. It gets hard to think of how this class, what its type is. Is it more a type of B or more a type of C? It's inheriting the functionality, which is useful for code reuse purposes. But generally, multiple inheritance in object-oriented programming is confusing. But we can do this. We can have some subclass here, which is a derived class, which gets the base class of one type and the base class of another, all inherited into it. And I picked this diagram here. It uses different names, so subclass is another term you'll see instead of derived class. Okay, we can also have different types of classes when we're talking about inheritance of abstract classes versus concrete classes. This will be a little bit more familiar with people who have Java experience because I believe they make this an explicit keyword. But in C++, again, we can have an abstract class which just serves as an interface and cannot typically be instantiated anyway. And we do this by making every function virtual or purely virtual. And then we can have concrete classes. That's objects that can be instantiated and usually derived or inherited from an abstract class, so something that sort of sets up the interface. Okay, so here's just terminology of abstract class versus a concrete class. So here's an inheritance diagram here. Again, with what we learned a little bit about UML here. So very clearly, I just want us to focus on these boxes here before we even look at the code. We have animal, and dog is inheriting from the animal class. Okay, and we see that some of these member functions, eat and make noise, are the same here as an animal. So it is overriding the functionality of the class that it's derived from. Okay, and C++ does this through the virtual keyword. Okay, so this class here, animal, this is our interface. It's sort of an abstract class. It has some default functionality for what it means to eat or to make noise, but the dog will override this functionality because it re-implements those member functions. Okay, great. So now with these two features, again, just understanding classes and sort of solidifying that, and then the inheritance available in C++, we should see about how we can use these features. Okay, so here's an example where you're running a restaurant. Okay, and we can start with a new coffee in this restaurant. We look at this, great menu here. We have espressos and lattes, latte with soy, cappuccino. I'm not too much of a coffee drinker, but this stuff still looks good for me. Thinking ahead though, I want to model this menu for our customers, and I can even start sketching out a generic drink class. So here's for our drink, how much it's going to cost and maybe the steps to make it. Okay, so at our restaurant, we want to add additional drinks on our menu: lattes, latte with soy, latte with caramel, all of these different drinks here. They all have this function in common, make. Okay, so as a little exercise, go ahead and try and see if you can draw this UML class diagram. See what happens. Try to see if you can implement, just at a high level, what each of these classes will look like. Okay, so go ahead and pause the video and take a moment to do that. And if you're joining back with us after doing this little exercise, Did you come up with something like this? Maybe you did. So you saw that maybe all of these different classes here, latte, latte with soy, latte with caramel, latte with soy caramel, etc., were driven from the drink class, or generic drink class, which is, some sort of espresso that can be made. So, thoughts now that I can think about is, how can we improve this class here, this drink class? I sort of wonder what can be done. So go ahead and pause the video and, how can we make this better? And what does better mean? Okay, so hopefully you had some time to think about that and pause the video. But better in this scenario might mean, less complicated, maybe less classes here being derived from the same base class. So certainly we can try to simplify things here. Okay, so we could do something like this, where we just have one drink class, and then we have all these different types. Espresso, milk, soy, caramel, hazelnut, and tea leaves. So our drink class is now composed of a bunch of different types, and then it'll return if it has milk, has soy, has caramel, has hazelnut, based off of all of these objects here. So I wonder, if you pause and think about this, what's the problem? And if you had a moment to think about it and pause the video, the problem here is that, a lot of these properties might never be used. Because if we want to make an espresso, for instance, caramel, hazelnut, and tea leaves, for instance, might be all wasted. Okay, so then we have all this extra data that we're carrying around with us, and our object's a lot larger than it needs to be. So one possibly better solution might be to try to decouple, this data so that not everything's tied together from our drink class. Okay, so decoupling is the idea that we want to reduce some dependencies in our software. That is, can we get rid of soy so that every drink we create doesn't have a dependency or change base of this soy class here? Okay, because these are each individual classes that we created. And, if we make one change in our software, meaning if I update the soy type or milk or espresso, it shouldn't affect the drink class. But we have a dependency here because all drinks consist of, caramel, hazelnut, tea leaves. So anytime I make a tea leaf change, a hazelnut, caramel, etc., you get the idea, it makes a change in our drink class. So that's typically bad. And this is also bad too because if we remove soy from our drink, it also affects all of our drinks if they have derived classes and so on. Okay, so there's a sort of a tight coupling there. Okay, so we try to fix this by having a balance of another technique called composition. Okay, so inheritance is when you're deriving from another class, but composition is when you have a class as a member variable in another class here. So this is how we model it in the UML. So milk, a latte has a milk, and a latte has a flavor. And a latte can be a drink that you can make and is a espresso. Okay, so this is the sort of relationship we like. It's a little bit less complicated. And again, you can play around with this to make it sort of as clean as possible. But we have to balance these ideas of composition, so what our classes are made of and what our classes are derived from with inheritance. Okay, so some final notes here, just kind of introducing these ideas of inheritance, composition, and so on, is to look at, again, the UML diagrams here. Here's sort of a cheat sheet for us where we can have an abstract class. Solid lines with arrows represent inheritance. So here's inheritance here, and this example here. Subclass to parent class is in the direction of arrow, so that means derived class from the parent class. And if the arrow is not filled, so this one's not filled, that means this is a totally abstract class. Okay, so these are all purely virtual functions here. A dotted line with the arrow indicates a dependency. So if we see a lot of these dependencies in our diagrams, this could be an indication of coupling. Okay, so here's a derived class which has perhaps a member function here that takes a class as an argument here. So that means it's dependent on whenever this class changes, this is going to be affected. And then the last thing that we saw with the composition, which is modeled here, is the diamond represents a has a relationship. So coffee class has a milk, as a member variable. Okay, and I've just made a quick update just to be explicit in C++ that if you want to make something that must be derived, it's a pure virtual member function, like so. Okay, so this member func has to be derived, has to be implemented in the derive class. Typically, this is a relationship, again, we like to see where derived classes are always derived from abstract classes. Might be hard to avoid sometimes, but this is what we like. Okay, so with that, we got a little bit more object-oriented programming experience. Go ahead and give yourself a break if you haven't been giving yourself breaks, because that's important. And then we'll continue on with the next session. Okay, so if you're joining us back, I want to dive into the topic of today, which is design patterns. Okay, so here's the deal. We're going to look at design patterns in sort of a fun way, in that you're hired as a programmer to perform some maintenance. So, we've been impressed with some of the work that you've been doing so far. And the software that you're going to be developing is a very exciting screensaver. Okay, you're going to get lots of money to do a good job, and you're going to be working on this project with a very large team. Okay, so if you do a good job, then you'll get another more lucrative contract. Does it sound good? Go ahead and sign the dotted line, and let's proceed. Okay, so your first day of work, here's what you're given. It looks pretty similar to what we were left off with, but it's a screensaver with a bunch of circles bouncing around. And our job's going to be maintain and improve this software. And we saw this last lecture, but the effect overall is quite appealing. But you're becoming a good programmer, and you sort of notice a few subtle errors. And in this example, all of the circles start out on a fixed portion of the screen. You can see it right here when the animation starts. And this is a bug. Okay. So you go bug hunting, and you've spotted a bug that generates the starting positions of each of the circles. Okay, this is in the circle class that we designed, and we noticed that all of the circles are generated at a random position of 300. Okay, so, or rather between 1 and 300. So I'm generating a random value, modding it with 300 to give me a range of 0 to 299, and then I add 1, so it gives me the range of 1 to 300. But, anytime you see sort of hard-coded values, that's a little bit of a red flag for you. You say, hey, where did this value come from? It's not described in the comments, so we don't really know. And you observe that the window size that we've created is actually 640 by 480. And that's stored into global variables here. But our range is only 300 to 300. So, we think the initial range must be much larger for these initial circles to spawn in our screensaver. Okay, so the first fix that you make for this software is just to change the values. Just update them to 640 by 480. You want to sort of solve the bug and impress everybody on your first day of work. So you do this. But, problem still remains, and I think you know better. In each of these spots, the bug really is just hidden from us. Okay? So again, so the bug's just really hidden from us. It's probably going to resurface again, especially if we update this window height or the window width in this scenario. So we need to introduce something else. It's a little bit more powerful called a design pattern. Okay, and certainly this is something that we can design better than just fixing these hard-coded values or resorting to this free hanging global variable. Okay, so design patterns. What's a design pattern? It's a common repeatable solution for solving a problem. There's sort of templates, or I like sort of thinking of them as flexible blueprints for developing software, meaning they're, things that have worked in the past. They're tested, they're known solutions. They're not guarantees or things that we can just plug and play, but they're good blueprints for solving common problems in software. And design patterns themselves can make programs more flexible, maintainable, or extensible. Well, some of the things we talked about that we need to work with when we have large software, we want it to be flexible and maintainable. And if we're working with lots of engineers, we want it to be extensible. So design patterns can really help us do this. And the origin of the term design patterns comes from architecture, actually, where folks thought about blueprints or patterns that could be designed. So there was an actual book called A Pattern Language here in the 70s that described various patterns on how to build buildings, make different architectural designs that were known to be good. And then along 1994, the design pattern idea really became popularized by this book, or at least it's the most well-known one in the last 20 or so years, from these four authors, Arik, Richard, Ralph, and John. And they're known as the Gang of Four, and this is thus dubbed as the Gang of Four book, who wrote this design patterns text that's popular enough to have a Wikipedia page, so it's quite popular. And it's really the best starting point for, or one of the best starting points for learning design patterns. Now, I also really like this game programming patterns book. I use it a lot in my game engines course. 4 different patterns applied to games, and this also has nice examples that complement the design patterns book. And it's free on the web if you want to check it out. As for this book, there's really 3 categories of design patterns. Creational, structural, and behavioral. And that's one of the key contributions of the book, that it provides us a way to build programs, and sort of think about 3 categories of design patterns, whether we're creating data, meaning creating the objects, and not having to think about how we instantiate them or their data types, structural elements, and just thinking about inheritance to build objects and get new functionality that way, or behavioral aspects in our software, the behavioral structure, meaning, well, what's our main building block? We talked about it being a class, and then thinking about how those classes talk to each other. Okay, so I'm going to help us pick the first pattern to solve our original problem with our screensaver. And this first one happens to be a creational pattern. We're going to look at 1 creational, 1 structural, and 1 behavioral pattern today. So creational design patterns, again, deal with how objects are instantiated. And they often abstract the process, meaning you don't have to worry about how the actual object's created. You just have to be able to use it, okay? So that means that functionality is encapsulated or sort of hidden from the client on how an object's created. How or what type of object's being allocated when you use the new operator. So again, here's the problem that we're trying to solve. We want to be able to reference the window width and window height globally. That way we only have one place where we really need to change it in our code. Okay, because again, we prefer not to maintain individual global variables like window width and window height, because these 2 variables, in fact, they're related to each other. We might compute an aspect ratio, which is common to do window width divided by window height. If you've ever bought a TV or just adjusted your monitor, the aspect ratio is important. There could be other different functionalities you want, but really they're related, so they should be grouped together in some way. And we should really only have one of these values. Okay, so a design pattern of this is called a singleton. And the singleton pattern enforces the existence of only one instance of an object being created. So that means we could have a configuration, for example, which stores all the values that we need or want to be uniform in exactly one place. Okay, so the singleton pattern enforces the existence of only one instance of an object being created and has it globally accessible. Okay, so some common uses for the singleton are things like managing files in a file system, right? You only need one of them. If you have resource managers, so if you're loading data in your software, for instance, you might use a resource manager to load, sound files, specifically your image files. You could have a logger that's logging bugs, for instance, in your program. Typically, you only need one of those, and they can sort of log messages in a centralized database. And then, of course, you could have a configuration manager that holds some global configuration value. And this is what we really want today. Okay, so let's do a little bit of refactoring. And our first step is going to be to move our global variables into a class. Right, that's our main tool in C++. I'm going to take these global variables, window width and window height, and move them into a class. This groups both the variables together, and we can also define some functionality for them. Okay, so here's the refactoring. I've taken these two global variables and moved them into a new class called Configuration Manager. Okay, and this Configuration Manager is going to be our singleton class. Okay, so let's take a look at the C++ in a closer way. We have these member variables here, m window width. Again, the m underscore is just to be explicit that these are member variables in a class. I've grouped them together here. And then I've written some getter and setter functions so we can access our private data as a client here. And we can get the window width and get the window height. And set the window width and set the window height appropriately. And then the real interesting part, or the part that comes from the design pattern, is this static member function here. Okay, so static in C++, when we use this in a member function, what it does, and this member function's name is instance, is it makes this accessible to all instances of the class Configuration Manager. So anytime we create a new Configuration Manager, this static member function is available to all those instances. Okay, so whatever it's going to do, okay, whatever data it's acting on. Now, the next line here, static, again, another use of it, makes this local variable here that we create, and because it's part of a static function that's available to all instances of a configuration manager, this configuration manager is always going to be the same for all of our configuration managers every time we call the instance function. Okay, static makes this variable shared across all instances of configuration managers. So if I create 1,000 configuration managers, this variable here will be the same for all of them. And what this variable is, it's a pointer, name it instance, to a new configuration manager. So it's allocating for the configuration manager, exactly one, and returning that instance to us of this configuration manager. Okay, and it's always, 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 because this is shared between all configuration managers, going to give us the same value. Now C++ does something a little bit weird here. Let me show you the equivalent code here. Vim config. I just want to show you that this bit here, so I could rewrite this in another way in C++. Instance here, static configuration manager, instance equals new configuration manager, and then return the instance. And just for clarity, if you want, this instance here is a different than how this is named. This is a member variable, this is a member function name. Now what I could do within this class, so let me go ahead and put it in the class here. Class, configuration manager, and so on, you know, all the same stuff. I could make a private variable here, make this all one data member, like so. And then I could rewrite this code if instance equals null, or null pointer in C++, then create a new instance. This code here is exactly doing the same thing as this code, but C++ 11 and beyond, which we're using, saves us some typing, but this is essentially the same exact code above. Okay. Okay, so that's the singleton pattern here. Okay, so this is just describing again what happens, and this idea here is exactly the same that we have here. Okay, So now we have encapsulated how an object's created and restricted creation to just one object of this type. Because again, this static here by C++ 11 and beyond is guaranteed to only instantiate one configuration manager. And since this is the same configuration manager, it's going to be returned every time the same instance of this object. Okay, so here's an example of how we utilize the singleton. Okay, here's our class. Here's an example. So I'm going to use configuration manager. The scope operator is telling me, well, within this configuration manager, find this member function, : instance. And then this is a static function, right? So it's shared across all instances of configuration manager. And then I'm calling the function set window width. Instance here, if we look, returns a pointer to the instance and the same one every time. So if I set width, I'm setting the width and setting the height of the same configuration manager across our program. So it's essentially a global variable. Okay, so here's how I can use it to set my window width and window height of my window. Okay, and then in my other circle class, I can now use configuration manager, get the instance that we always get, and get the window width and then the window height. Okay, because we're always accessing information through instance, all the data will be the same. Okay, so let's see if this solves our problem. And we let it run, and it does. Okay, so if you watch this a few times, you'll believe me and see that these circles can be spawned in any location across our screen here. Okay, I'm going to let it just start one more time so I can see if the problem's fixed, and you should see circles all over the place. Perfect. Okay, so success. Wrapping up the singleton, but again, we want to be good software engineers and understand the pros and the cons. So the pros are, overall, this is an easy implementation. It's effective when you know you're only going to need one of something. We're not creating a bunch of global variables. We call this, polluting the global namespace if we just have lots of variables, window width, window height, that are sort of around in our programs. And then memory is only allocated if you actually use a singleton, right? Only if we construct one of these singletons here does it actually get built. Okay, the cons, wrong usage could take some refactoring, meaning, if we really didn't need only one configuration manager and we find out we need 2 or 3, we have to break this pattern and re-implement some classes. When we talk about multi-threading, this isn't thread safe, so you're going to have to add a lock if there's any shared data. That might slow down your program because you're adding locks on a shared resource. And you're still effectively using globals in this sense, which we might try to discourage again for performance. Okay, some of the missing details, and you can read the Gang of 4 book for this, but we have to again think about what our clients might do with this information, or with our implementation rather, meaning we might also want to hide the copy constructor to make it non-copyable. You'll notice in this singleton, where is my constructor and my destructor? Well, they're hidden. They're in the private section of my class. So I can never actually construct a configuration manager because I've hidden the constructor here. The constructor and the destructor will never be called. So the only way, again, to construct a configuration manager is through this instance member function. So that's pretty cool. But if I make a copy or reassign this object, I could, in fact, make a copy of something that I'm only supposed to have one of. So I would probably want to hide the copy constructors too. Again, this is sort of the advanced section of the singleton. Thread safety, again, might be an issue. We can use locks, but we have to be careful about this from a performance standpoint. If we do need multiple instances of the class, there's other patterns. There's something called a mono-state pattern that we might want to take advantage of, which uses static member variables. Now, static member variables are variables shared across every instance of class. Okay. And then finally, this is, again, nuanced C++ details, but we have to be careful to return a pointer versus a reference from our instance function, okay? Because if we return a pointer, again, that's something that can be copied. It can be copied or pointed to. But even worse, it can be deleted because we can delete memory that's pointed to. Okay, so that's why we return a reference here. And this reference is to the actual instance. So instance, we've allocated memory. We dereference it, so it's the actual instance, and then we reference that here. Okay, so more on the singleton pattern. I would recommend, if this was too much for you, you go ahead and click this link on the game programming patterns and read through the singleton pattern here. It's a nice read. It'll take about 15 minutes to read through, and then maybe 15 minutes to look at the code examples and really try to understand what's going on here. And this is another perspective on it. Okay, so on to the next challenge, on to our next design pattern. Now this time, our boss wants us to put the company logo on every screensaver. Something like this, screensaver company. But your colleague is working on the actual legacy text rendering interface. That is, how do we draw this screensaver company logo here? And, if we want to actually write this font, the text rendering involves quite a bit. Loading font files, a custom string class, drawable object class, some deep hierarchy just to get this string here shown, this piece of text. And oh, by the way, your boss adds these additional requirements here that the text must always be green and uppercase letters. Okay, so here's the problem that we're solving. We have some text that must always be uniform. Some text here, screensaver company. And it's based off some legacy or third-party text class. In our case, it's from the Simple Fast Media Library. It's a third-party library. And there's a lot of steps needed to fit our specifications. So one possible solution we could use is to write a function we can pass all objects through. But, what if we need to modify other behaviors, like how we draw the text? So in this case, we could write a function here called adapt text that takes in the original text and, sets the color and so on. But if we want to add new behaviors, how do we exactly do that? So in order to handle this challenge, we're going to introduce a structural design pattern, our second category of design patterns. The structural design patterns focus on using inheritance to compose interfaces and create new objects. Usually they're focusing on inheritance, but sometimes we can use composition as well to create new objects. And I'm going to show a pattern called the adapter pattern. I'm going to show a specific instance of it called the object adapter pattern. Okay, so the adapter pattern, as it looks, it's an adapter, and it converts one interface of a class into another interface the client expects. So here's the pattern: converts the interface of a class into another interface the client expects. So the common uses are writing wrappers to update or otherwise make an interface work. So we want to write a wrapper, for instance, to make our text work as expected. You'll see wrappers for updating legacy code bases, making various string classes work together. Anytime you need to adapt a class to work in a new way is when you'll use the adapter pattern. Okay, you can just the analogy works great if you've traveled to a different country that has a different voltage or current on their wall outlets. So if you travel to Europe and use a US power adapter here, you need our standard plugs, you need a AC power adapter to change the current. Okay, so this is the example. We're going to write the adapter class here. Okay, so again, here's the problem we're solving. We have a class that does, not quite the functionality we want, this SF class here. And we want a simple way to update our software without breaking the old functionality. We don't want to have to rewrite this class, SF text, because, well, we don't have the source code to it. This is Simple and Fast Media Libraries code. So our first take of the adapter pattern is to write a new class called adapter text. We're going to use composition, that is, make this SF text a member variable in our class here. And then our constructor of our adapter text is going to take as a parameter a text here. Okay. Now we could use inheritance again, but let's make some assumptions here that SF text might be in a deep hierarchy, and we might want to change the functionality further. So this is one way to solve the problem. Okay, so here's the implementation in the constructor, as well as the new behavior to draw our text. So here's what our constructor looks like. It makes a copy here of the text that we pass in, and we may or may not want to do this, but we're making a copy, which is fine for this example. And we take in the copy of our text, which we store in m_internal text. That's our member data here. Set the appropriate font size, set the color, and then we sort of handle our behavior here for uppercasing our entire string. And that's the adaptation going on in the constructor. And then the additional functionality that we add in our member functions here is how to draw our new adapted text. In this case, we're just drawing the internal text here. So if we do this, we get a quick wrapper class, and every time we run this program, we get screensaver company. It's all in green, it's all uppercase, it's the right font size. We are good to go. Okay, so some pros and cons of this pattern, the adapter pattern, is that it allows classes with otherwise incompatible interfaces to work together. We can just make things work as they should be. And it can work very quickly. So, we had something that almost did what we wanted, but now we can ensure any time that we need to show the company logo, we just pass it through this adapter text, okay, from our legacy system here text. The cons of this pattern, though, because again, we have pros and cons for each of them, is that it might introduce more complexity into our code. If you use, if you already own all the code, it might be worthwhile to just update that class to do what you need it to do. But if you don't, consider the adapter pattern. In my particular example, again, what I showed was I was making an additional copy to wrap an object, and that could be expensive. So you might think instead about using inheritance in this pattern. You can do both. Okay, I showed one example with composition. Okay, so your next task, final pattern for today, is that now your boss wants to fine-tune the screensaver just a little bit. And I think it can be improved by adding more circles, right? This screensaver is kind of boring here. So first, refactoring. You search the code, and you start finding for loops that look like this, because you need to add more circles. And you say, okay, in this loop, I'm creating a vector, which is a container data structure of all these circles, and I'm going to loop through 100 times and push in a new circle. Okay, I'm going to do that 100 times. Then you see later on in your code something corresponding to loop through 100 elements and get the window size here. Update your circles appropriately based off the window X and Y size. This is setting the bounds. And then to draw the circles 100 times because you have 100 circles. The quick fix, you say, is, well, that didn't look quite right here. We already found out this is a problem if we have variables here. But, we know in the vector class, there's a handy .size function that'll tell us how many items we've pushed into this data structure, this sort of container. And, now we don't have to worry about having different values in different places. Okay, I less than circle .size. Okay, and this is great, but we can do better. Okay, so now I want to introduce a behavioral design pattern. Behavioral design patterns, again, are third category, focusing on communication between objects. Okay, but they're really concerned with algorithms and the responsibilities between objects. And the relationship I want to work with in this example is how an object and a collection is linked and how to traverse them. Okay, so the third and final pattern for today that I want to talk about is called the iterator pattern. And the iterator pattern provides sequential access to elements in a collection without exposing your representation. Okay, so here's the problem. We have some data structure, something that you've learned about, in some type of collection. How a collection is just how we're storing the data. So it could be a linked list, hash table, array, map, unordered map, vector, etc. Just a plain old array, standard array, and so on. And at some point, a user might want to look at all of the data in our collection. So the solution is we can encapsulate the iteration to ensure we have a consistent way to look through our data. Perhaps from the first element to the last, or maybe reversed from the last element to the first. Okay, or maybe in some other traversal, right? If we have a more complicated data structure, right? There's sort of this nice analogy here. How many possible traversals are there of Rome? You can sort of walk Rome. You can, follow some other path that someone's laid out. You could use a GPS. You could take a tour. There's lots of different ways that you could travel Rome. How are you going to iterate through and visit all of Rome? There's many. So our first take at what's called the iterator pattern. And the good news about this one is, for the most part, in the standard template library, we get these for free. So if you use any of the standard data structures, ones that start with std : that means the standard library. I didn't implement anything here, and you get those for free. Okay, so within our vector, so I'm refactoring this code to this code below, we can take a standard vector, and this is a template. We have to talk about templates more, but it just means the generic type is a circle, and then : so a member of this vector, and it's a static member. That's how we're accessing it here. It's iterator, equals circles.begin. So the beginning of our circles collection. Okay, we create this iterator it. And while it is not equal to circles.end, which is the end of the iterator, move our iterator forward, iterator ++. Okay, so what this is doing is enforcing the order of our traversal. It says, hey, we're going to start at the beginning every time, and until we've reached the end, we're going to move forward one item in our collection. Okay, so it doesn't look like we've made much improvements from what we have here. We're doing the same thing. We're just starting from 0 and moving forward. But we're very clearly describing what we want to do with this iterator pattern. Because here at line 75, we're saying I equals 0, but why 0? Do we always move from the start? Or did I just choose to this time? So 0 is another magic number. This very clearly states we want to start at the beginning every time in our iterator. Because you could take an index that theoretically started at -5, or if this is a map data structure and you're wanted to start looking at -5 or something, this could be possible, but this very clearly says you want to start at the beginning. Here, it says we want to go very clearly to the end. And it prevents us from making little errors here, like dot size. Was it dot size -1? Was it dot size +1? We don't have to worry about that. We just say go to the end and move forward one item at a time. Removes chance of making a typo here. So the iterator pattern is very powerful for preventing bugs, and it's very expressive, telling us exactly what we want to do. So we should always use iterators when our intent is to move through the entire collection, one element at a time. And here's our result. Beautiful. We increase our circles to 1,000, and we have a lot of them here, and it's pretty cool to look at. And we've also made our code much more maintainable. We can change the underlying data structure, whatever, to do more powerful things. Again, there might be different iterators that you want to use that can be even more powerful, and so on. Okay, so with that in mind, iterators are something you should consider everywhere when using standard template library data structures, and you get them for free. So there's no reason not to use them. Pros and cons of iterators. We like them because there's something known as a single responsibility. It's very clear what the iterator is doing. It's just moving you through the collection one element at a time. This is called the single responsibility principle. It makes it very easy to understand what the code's doing because there's only one job or one thing to understand. Iterators move through data. Robust iterators as well, depending on the implementation, can also protect you from other things. For example, and a lot of these things happen when you have multi-threading, but it protects you. What if you're iterating through a collection, even this same collection here, circles.size, but you have another thread come in and remove one of these circles from your collection. A good iterator will protect you from that, meaning while iterators taking place, or while iterations taking place, you can't remove an item. Okay, so that's something to consider. Now the cons of the iterator pattern are, applying the actual pattern might cost some performance, especially if we're just iterating through simple data types like numbers or whatever. Creating a whole iterator and then, moving the pointer every time could have some performance cost. So you'll have to just measure that. Okay, so the summary here for today is, we've looked at a small project where we can, where we have different applications of 3 design patterns: singleton, adapter, and iterator. And we've seen how they can solve some of our problems, make our software just a little bit better. And over time, especially in a really big project, these little incremental fixes make a big deal to us and can matter quite a bit. But the design patterns themselves aren't a magic solution. With every one, I showed that there's a con for every pro there is, roughly. But they might be good starting positions to solve our problems. Okay, so my recommendation is to continue learning more patterns and apply them to small projects and test out their utility. We'll certainly get some practice in this class. Okay, so with that, you'll have an in-class activity and then a lab. All right, and I will see folks in the live class.